Welcome to another video by Adeptis Academy. You've heard the term ballistic missile in news reports and documentaries. It's a term often associated with global politics and military strategy. But what does it really mean? Let's break it down. At its core, a ballistic missile is a rocket-powered weapon that relies on powerful engines to generate thrust. It follows a high, arching path, called a ballistic trajectory. This trajectory is predetermined and largely unpowered for a significant portion of the flight. Think of the arc a baseball makes. A ballistic missile follows a similar but much larger path. It gets a huge push from its engines at launch, generating immense speed and altitude, then coasts unpowered, letting gravity and momentum guide it to its target. Unlike cruise missiles, which fly like airplanes, ballistic missiles are more like a stone thrown across continents. Intercontinental ballistic missiles, or ICBMs, are designed for long-distance strikes. ICBMs can travel over 5,500 kilometers, reaching targets on different continents. They soar high above the atmosphere, even passing through space before re-entering, experiencing extreme heat and pressure. In short, a ballistic missile launches a payload on a precise, gravity-driven arc to a distant target. It's arcing like a thrown stone, but with incredible speed and accuracy. Understanding this basic idea is the first step to grasping the science behind these powerful machines. So, how does a ballistic missile begin its incredible journey, arcing across vast distances? What are the key steps involved in transforming a dormant missile into a high-speed projectile? It all starts with a massive, carefully controlled explosion. This isn't just any explosion, it's a precisely engineered event designed to unleash tremendous energy in a specific direction. This explosion ignites the rocket engines, generating immense thrust to overcome the relentless pull of gravity. The force has to be precisely calibrated. The missile might launch from the relative safety of a hardened underground silo, a hidden fortress designed to withstand attack. Or it could be fired from a mobile truck, offering greater flexibility and concealment, or even from the depths of the ocean, launched from a submarine, adding another layer of stealth and surprise. The engines create a powerful torrent of superheated gas, blasting downward with incredible force. This intense downward pressure is what propels the missile skyward. It's Newton's third law in action. For every action, there is an equal and opposite reaction. A large ICBM, or intercontinental ballistic missile, can weigh over 100 tons. That's equivalent to a fully loaded semi-truck. So the engines must generate significantly more thrust than its immense weight to even begin to lift off the ground. The initial launch is deceptively slow at first, a gradual push against gravity's relentless grip. But the missile quickly accelerates to supersonic speeds, leaving a trail of fire and thunder in its wake. This initial period of powered flight is known as the boost phase. It's the only time the engines fire, making the missile most visible to detection systems, and therefore the most vulnerable to interception. In just a few short minutes, the missile's guidance system must calculate and achieve the perfect speed and angle. This is crucial to ensure it hits a target potentially thousands of kilometers away with pinpoint accuracy. Think of it like a quarterback's throw in football. The launch window is brief, but everything hinges on getting the initial trajectory and velocity just right. Once the engines cut off, the missile's path is irrevocably set, and it transitions into unpowered flight. The boost phase is relatively short compared to the overall flight time, but it's undeniably the most critical part of the entire journey. Next, let's delve deeper and examine what happens to the missile during this powerful and crucial ascent through the atmosphere. The boost phase showcases the power and precision required to propel a missile skyward. Most long-range missiles employ a multi-stage design for greater efficiency and extended reach. These missiles shed empty fuel tanks as they ascend, becoming progressively lighter and faster. Each stage ignites in a carefully orchestrated sequence, boosting the missile to incredible speeds. These speeds can reach up to 7 kilometers per second. The engines mix fuel and oxidizer to create the necessary combustion. Some missiles utilize liquid propellants, offering precise control over thrust and direction. Others rely on solid propellants, providing a simpler and more reliable solution. The ultimate goal is to reach the burnout point. This is where the engines shut off, and the missile is set on the perfect trajectory. The guidance system is constantly monitoring and adjusting the missile's orientation. They are what makes intercontinental reach possible for these incredible machines. The boost phase is relatively brief, but it's during this period that the missile's entire journey is determined. With engines off, the missile enters the midcourse phase, the longest part of its flight. Now it's a high-tech cannonball coasting through space, guided only by momentum and gravity. For ICBMs, this is when the missile releases its payload, often multiple warheads, each aimed at different targets. This is called MIRV, Multiple Independently Targetable Re-Entry Vehicles. The missile may also release decoys and chaff to confuse defenses. The midcourse phase can last up to 30 minutes, with warheads and decoys streaking across the globe at hypersonic speeds. Ground-based radars track these objects, and missile defense systems try to intercept them. A cosmic game of billiards. The missile's job is done. It's delivered its payload to the right spot in space. Now, gravity takes over, pulling the warheads toward their targets. The next challenge? Surviving the fiery plunge back to Earth. The missile's arc is a suborbital flight high enough to reach space, but not fast enough to stay in orbit. Its path is set by launch angle and burnout velocity. A 45-degree angle is usually optimal for maximum range. Newton's laws of motion and gravity predict this arc with stunning accuracy. Engineers must account for Earth's shape, gravity variations, and even the pull of the sun and moon. The missile's energy shifts. Chemical energy becomes kinetic and potential energy during boost, then back to kinetic as it falls. This elegant energy exchange defines the missile's journey. The science is pure classical mechanics, centuries old, but still at the heart of modern rocketry. Now, the warheads are racing back to Earth at incredible speed. Re-entry is the most intense part of the journey. Warheads slam into the atmosphere at hypersonic speeds, generating heat hotter than the sun's surface. Without protection, they'd burn up instantly. Re-entry vehicles use cone shapes and special heat shields. Either heat sinks or ablative shields that burn away, carrying heat with them. As they descend, air resistance slows them, but they're still moving at several times the speed of sound. The plasma sheath around them makes tracking and interception extremely difficult. Some advanced warheads use small fins or thrusters for last-second course corrections. After thousands of kilometers, accuracy depends on everything going right, especially during this final fiery minute. The warhead's journey ends in a pinpoint strike. Let's see how guidance makes this possible. How does a missile stay on course? That's the job of the guidance and control system, the missile's brain. Most use inertial guidance, accelerometers, and gyroscopes track every movement from launch, with no need for external signals. The onboard computer constantly compares the missile's path to its programmed course, making tiny adjustments as needed. Control systems steer the missile using gimbaled nozzles or small fins. Some missiles use star trackers, tiny telescopes that recognize star patterns for extra precision. All these systems work together to ensure the missile is on the right path when the engines cut off. After that, the missile coasts, its fate sealed by the guidance set during boost. Even a small error early on can mean missing the target by miles. Modern guidance systems are marvels of engineering, enabling pinpoint accuracy over intercontinental distances. Precision is everything, especially when the stakes are this high. Now, let's talk about safety and the rules that govern these powerful weapons. Ballistic missiles are tightly controlled by safety systems and international agreements. Permissive action links, or PALs, are security codes that prevent unauthorized arming of warheads. Treaties like SALT and START limit the number of ICBMs and require verification through inspections and satellite monitoring. The Missile Technology Control Regime restricts the spread of missile technology among nations. These rules aim to prevent accidents, unauthorized launches, and the global spread of these weapons. The science is neutral, but the consequences are enormous. That's why international cooperation and safety protocols are so crucial. Now let's recap the entire journey. Let's recap. A ballistic missile launches with a burst of rocket power, guided precisely during the boost phase. It coasts through space, releasing warheads and decoys in the midcourse phase. Gravity pulls the warheads back to Earth, where they survive re-entry thanks to advanced heat shields. Guidance systems ensure pinpoint accuracy, while safety protocols and treaties aim to keep these weapons under control. The science behind ballistic missiles is a blend of physics, chemistry, engineering, and international law. Understanding how they work helps us appreciate both the power and the responsibility that comes with this technology. From a simple thrown ball to a global journey, it's a story of human ingenuity and caution, and that's the breakdown.